again. So let me just kind of give an introduction to why we're going to be studying linear systems, why they're significant. Oftentimes, as we've seen in algebra, we're looking for one missing number. But sometimes we're looking for more than that. And a good section to look at where you get these kinds of problems, and we're going to look at a lot of these, is in section 3.2. Why would we want to solve for two variables instead of one? Well, the key thing for solving for multiple variables, let me switch on the chat. The important thing to keep in mind is that if you have two variables, you're going to need two equations. So to solve for two variables, you're going to need at least two equations in order to get numbers for those variables. And situations like this come up, and I'll give you an example of a story problem. Let's see here. Let me find one that's a little more. Here we go. Now, you've actually done this before. And when you've done this, say in Math 097, you typically used a substitution method to get around it. You just didn't realize it. So let me give you an example of what I mean. So looking in section, let's say you have something like this. Account A. So what happens in this type of question? We can model this different ways, and there's a way you could sort of do this, the substitutions. But let me show you, approach it from a different point of view. Account A earned $200 in interest at a rate of 10%, and account B earned $50 interest at 5%. So if the total amount of money invested was $3,000, how much is in each account? So what we have is this. In fact, let me backtrack a little bit. I think I gave out too much information. Let me change the information a little bit. So let's still have 3,000 invested. account A at 10%, account B at 5%, and the total interest is $250. So let's say we don't know how much each account earned. Let's step back a little bit. So the way you earn interest is you take the interest rate as a decimal, you multiply it to the amount in the account. So let A be the amount in account A, and B is the amount of money in account B. Now we know the total amount of money that's invested is $3,000. So that means A plus B equals $3,000. And now the interest that's earned from A is 10%, so 0.10 times A plus the interest earned at B, 0.5 times B. Well, that total interest is $250. So now again, I've gone back and modified the problem where we didn't know how much interest came from each account. But let's say we know this much. We know the total amount invested. We know account A has a 10% rate. We know account B has a 5% rate. The total interest earned is $250. So what we do is we could say A is the amount of money in account A, B is the amount of money in account B. So the total amount of money invested, that's going to be amount in A plus the amount in B, that total is going to be $3,000. Now the interest in account A is the interest rate as a decimal times the amount of money in account A. The amount of interest from account B, interest rate times the money in account B. And if we take the amount of interest from B, add it to the amount of interest from A, that's going to be $250. So again, I modify the data here to make a more challenging situation, a more relevant one. So the thing is, can we figure out how much money is in each account, given we have these two equations to work with? And we can. So we're going to take a look at some of those techniques today. So first off, when we talk about systems of equations, we're going to talk about what a solution is. Now, a solution to the algebraic equation so let's say we have this. If we solve for x, what we're going to get the solution to x equals 2. So that's what we're very familiar with. When we work with systems of equations, the solutions are going to be different. Instead of x, the solution will be two variables, x and y. So one of the things we might ask is a solution, a pair of numbers, going to be viable or valid for a system of equations? And so we've seen this a little bit with the, you can do this with, say, an equation of one variable. So the way we figure this out, replace x with 3. Does this, in fact, equal 9? Well, if we do the order of operations, well, clearly no. So x equals 3 is not a solution. So that's how we work with one variable. With two variables, what we're going to do is we'll have an x and a y. And we're going to test the x and y in both equations. Now we have to be careful here. The x and y have to work for both equations, not just one of them. So xy must work for both equations, not just one. So we got to be careful. We can test x and y in one equation, and it looks like it's working. It's going to be good. But then we get to the second equation. It's not going to happen. Let me do an example. Now, let's say for this, we're going to determine is -3 to a solution. Now, again, we want to be careful with -3 and 2. We want to remember, -3, the first number is always going to be x. Always going to be x. The second number is always going to be y, unless someone tells us something different. We might have, for example, an equation where this is a t and this is a d, this is a t, this is a d. And we want to make sure someone reminds us or tells us that this would represent t and this would represent d. So sometimes they got to explicitly tell you, clearly tell you what they mean. But when we're dealing with x's and y's, we're going to follow the convention that x is always the first number, y is always the second number. So let's test this solution. Let's see if it works. So for the first equation, x is -3, y is 2, and does this equal -7? Well, the answer is going to be no. Oh, I see. Yeah, that won't work. So what we're going to get is 1 does not equal -7. So right away, this isn't going to work. We know this is not a solution. So let's try a different one. Let's change things up just a little bit. So -3, 2 didn't work. What about -3, -2? So now I put a negative here. Well, is that going to change things? Well, again, x is -3. Now y is -2. Does this equal -7? Well, what we're going to get, -3 plus -7. I'm sorry. Getting ahead of myself. Does this equal -7? Well, certainly it does. So far, so good. But this here, we have to be careful. This is only for the first equation. We have to check the second equation. So let's find out. So again, x is -3. -3 times -2. Does this equal 0? Well, 2 times -3, -6, minus 3 times -2, -6. Is this going to equal 0? Well, here's that double negative. This does equal 0. So since this ordered pair works for both equations, then we can say is a solution. So we tried -3, 2, and that failed right off the start. -3, -2 worked for both equations. Let's try one more. Maybe there's another solution. Let's go with this one. Is 1, -4 a solution? Well, plugging this in. X is 1. Y is -4. Does that equal -7? Well, 1 plus -8. And sure enough, it does. We'll get -7 equals -7. So far, so good. This one worked for the first equation. But we're not done. we've got to check it for the second equation. If it doesn't work for the second equation, it's no good. So for the second equation, 2 times x minus 3 times y, will this equal 0? Or 2, and we can say this is minus 3 times negative 4, negative 12. It doesn't look like it's going to be 0. Double negative. No way. We'll get 14. It does not equal 0. So it doesn't work. So we had high hopes. It worked for the first equation. It's not coming through for us on the second equation. So that means, though it was halfway there, 1 negative 4 is not a solution. So it's not going to go. Now, I've talked about solutions, and so far, what we've looked at is we ended up trying 3 different points: negative 3, negative 2. I'm sorry, negative 3, 2, then negative 3, negative 2, and now 1, negative 4. And the second one turned out to be a solution, and I kept looking for others. So how many solutions could you actually have? Well, there's 3 cases. And we're going to get into this a little bit more. You can have one solution. You can have infinitely many solutions, or no solutions. So why is this the case? Well, the reason has to do with the kinds of equations we're working with. And the reason these equations are significant is they're lines. So what we're looking at in section 3.1 are linear systems. What's important about linear systems is that each equation, in terms of x and y, represents a line. So let's take a look at the example we just saw. Each of the equations we can make into the familiar form of a line. So let's take these 2 equations. So in each of these equations, I'm going to solve for y. remember, I'm dividing both sides by 2, not just an individual term, though on the left side, the side is only an individual term, so by coincidence, that's what I'm doing. I'm actually dividing everything here by 2. And since I'm dividing everything here by 2, and there's a rule that lets us break this off. Actually, let me take a step back here. We can write it like so. But a more common way of writing it is like that. Either form, they're going to mean the same thing. So this is why, and I'm just going to switch the order on things. But this we just turned in to that. So this is just a line. This is y equals mx plus b. It's just a line. And same with this other one. Or we would typically write this as 2/3 x equals y. Or using the symmetry property, we can write y is 2/3 x. Now this is y equals mx, and then b in this case is equal to 0. But the moral of the story here, when we're working with these linear systems, and in section 3.1, those are the only systems we're going to be working with. We won't be working with non-linear systems. That's for another time. With linear systems, we're always dealing with lines. Now, what does this have to do with the number of solutions? Well, as I mentioned earlier, solutions, there's only 3 outcomes. You have one solution, infinitely many solutions, or no solutions at all. So if we graph these lines, how they interact will tell us about their solutions. So where they intersect is going to be the solution. And with lines, there's only 3 ways lines can interact. The first way is they can intersect. Lines can intersect once. And when they do that, you get one solution. Now, the other way lines interact is if there's one on top of the other. And when one line's lying on top of the other, there are infinitely many intersections. And so this means there are infinite solutions. So when one line's on top of another, it basically is saying that 2 equations both represent the same line. They might just look a little different. And we'll do some examples of these. Finally, we could have parallel lines. They never intersect. And since they never intersect, there's no solution. So any questions about this? So the main idea is this: with linear systems, they have solutions. We can take an ordered pair, an x and a y, substitute those into both equations. And if the ordered pair works for both equations, it's a solution. Now, there's only 3 kinds of situations we're going to deal with solutions. The first kind is there's only one solution, period. And that means the equations we're solving, they are actually 2 different lines that intersect at one point. And that one point is the solution. All other points aren't solutions. The other situation is that the 2 equations we're working with, they really represent the same line. And so when we graph these, you just get one line on top of another, and there's infinitely many intersections. All the points, they're crossing each other all the time. So we have infinite solutions. Finally, these 2 equations we're working with, they might represent 2 different lines but with the same slopes. Two different lines with the same slopes are parallel lines that don't intersect. Because these two lines don't intersect, there's no solution. So let's go back to our first example. Now I solved for the equations earlier, and we got y equals 1 half x, negative 1/2 x, minus 7 half. Let me see that. I might have forgotten my negative there. I think I forgot the negative on my 7. I apologize. So this should be the line that we have with that negative sign there. I forgot the negative sign that was up here. So take a second to amend your notes, make sure that negative sign is going to be there. And then for the other equation, we got this one. So let me bring back that other one. So if we put these in y equals mx plus b form, right away we're going to notice two things. One, these are different lines. This one has no y-intercept. This one has a y-intercept of negative 7 halves. The other thing we're going to notice, different slopes. A slope of 2/3, a slope of negative 1/2. So what that's going to mean, there are two different lines with different slopes. They're going to intersect at some one point. We just had to figure out where. So the way we do that is we just graph. So for the first equation, oh, actually, it was negative 7 halves. I'm sorry. Let me change this a little bit. Whew. Actually, there's a better way of doing this, I think. I'm going to try a different method of graphing these. I'm going to go with intercepts instead. And there's a reason for this. So instead of using y equals mx plus b, I'm going to go with intercepts. And to do intercepts, I think it's just going to be easier to do. So for the x-intercept, we let y equal 0. And so we'll get x plus 2 times 0 equals -7, or x is -7. So for the x-intercept, -7, 0. And then for the y-intercept, so I'm going to list these up here. So there's an x-intercept. For the y-intercept, okay, y is -7 halves. So that means -7, it's going to be 0, -7 halves. Or if you want, 0, -3.5. So here's the x, and there's the y-intercept. So for this one, the x-intercept, we'll let y equal 0. So 2x minus 3 times 0 is equal to 0, or 2x equals 0, or x equals 0. So here I'll back up a bit. And then x equals 0. Y-intercept, you're going to get the same thing. Because when we solve this for y equals mx plus b, we got a y-intercept of 0. I'll go through the steps anyway, just sort of a review. For the y-intercept, again, x is 0. Divide by -3. We'll get y of 0. So sure enough, 0 and 0. So now we graph these. Got here to -7. Sorry, it's kind of small. I'll do another example where it's a little more boxed in. So let's say we have, for the first line, the x-intercept was -7, 0. And the y-intercept was 0, -3/2, or 0, -7/2. And let me see, let me find it. I think I have a straight edge. Ooh, I think that made its way home. So a line looks roughly like this. Pardon my line drawing. So this was going to be next. We're going to do the 2/3 one. Now that's kind of a downfall because we just have 0, 0. But we do know the slope was 2/3. We do know that. So what we can do is start from here, go over 3, up 2, and then we can actually, this is kind of a questionable thing, you could actually go down 2 over 3, but I'm just going to draw the line through. So if you look at where these intersect, well, it's at the point -3, -2. Well, -3, -2 was the solution that we tested that worked for the system of equations. So if we graph the lines, where they intersect will give us that solution. Because if you're going to guess a solution, you're going to be guessing amongst infinitely many possible points. But here we can actually graph and find out what point is actually the solution without having to guess. So I'll do another one. Let me check our time real quick. 1:52 here. I'm going to open my door and get some fresh air. All right. So let me pick another one here. So let's say we have this. So, and let me make this a little different. Let me make this 6. It'll be a little manageable. We'll see what this does. So, in fact, let me even change it a little more. Let's go with this. Oh, I gotta be careful making these changes. Sorry, let me make sure this is gonna make good sense. Let me try to do a different one. Sorry, I'm having a kind of an off Thursday today. Try to be a little more consistent. So let's say, let me think a better example. The reason I'm so hesitant is the graphing is sort of limited on the board, and I just want to make sure I pick a good one that's good to graph, one that's kind of a bad one to graph. Here we go. This will work. So we could do this using intercepts, or we could solve for y. So x plus y equals 4. Subtract x from both sides. So we get y equals 4 minus x. Or we could say this is y equals negative x plus 4. So we can call this. That we'll leave that the way it is. Sort of construct the system where y has been solved for. Add 2y to both sides. Subtract 2 from both sides. So now we're going to have same system, but in this case we solved it for y, but it means the same thing. It's the same lines. So now I'm going to do this. I'm going to call this minus x plus 4. They mean the same thing, but this just puts it more in the y equals mx plus b form. So if we graph these, well, let's graph y equals minus x plus 4. So mx plus b. B is going to be 4. And for the slope in this case is negative 1. Or we always plus a, when you have a whole number, in this case an integer actually, place a 1 in the denominator. So this is the rise, or in our case it will be a fall, and this is the run. So we can fall 1, run 1, fall 1, run 1, fall 1, run 1, fall 1, run 1. Again, with my sort of questionable artistry here, it's going to be a little bit of a crooked line. I'm just going to try to blend the line. It's a little crooked, but it'll serve our purposes. For this next one, x minus 2, you can think of this x plus negative 2, where b is going to be negative 2. And then in this case, m is going to be 1, or 1 over 1. So the rise is 1 and the run is 1. So rise 1, starting from our y-intercept. Rise 1, run 1. Rise 1, run 1. Rise 1, run 1. You can rise another one, run another one. And if we connect these points, we're going to get another crooked line. But we're going to see the lines share one point in common. And that's the solution. So any questions about that? So let's see, about 15 minutes. So I'm going to go over the situation where you don't get a solution, or if you get infinitely many solutions. And we might not get to the algebraic techniques until Tuesday. And those will segue into the second section. Those are going to be used in the second section anyhow. They'll use in this section too. Let's see. You only have that example, but I'll do one. So let's say we have this. So let's say we try to graph these lines. If you take this one, let's put it in y equals mx plus b form. So subtract 4x from both sides. Divide both sides by 2. So we get y. Negative 6 divided by 2 is negative 3. And negative 4 divided by 2, negative 2. Or we can write it as negative 2x minus 3. So negative 2x minus 3. So I'm going to put this as the beginnings of a new system. Well, same system, just looks differently. So let's solve this next line for y, putting everything in y equals mx plus b form. Now notice what's happening with this. We get the exact same line. Now, how is this possible? We have two different lines, two different equations, but they reduce down to the same line. Well, one way you can tell, if you take this equation and multiply the entire left side and the right side by 2, 2x times 2 is 4, y times 2 is 2y, negative 3 times 2 is negative 6. So even though they look different, this equation is just 2 times this equation. Since you're multiplying both sides by 2, to reverse that, divide both sides by 2, and you're back to where you started. So this equation is just this one in the disguise of a times 2, which reduces down to the same line. So if you were to graph these lines, well, you're going to be graphing one on top of the other. We have a y-intercept of -3. We have a slope of -2. So we fall 2 and we run 1. And then for both lines, I mean, it's just one line on top of another. They're the same thing. This gives us the infinite many solutions. So the last one I want to go through no solutions. Make this a little more interesting. So same thing as before. We're going to solve for y. Or you could use intercepts, either way. Or I could reorder these. So there's the first one. Well, let's take a look at the second one. And if I reorder these, so when we put these two lines in the y equals mx plus b form, what we get are two different lines, but they have the same slope. So this means you're going to have parallel lines. Now for the first line, we have a y-intercept of -1. And in the draw second point, we have a slope of -2, or -2 over a +1. So we're going to have a fall of 2 and a run of 1. So fall 2, run 1. And then we can repeat this. Fall 2, run 1. Fall 2, run 1. Now I'll connect these. Now let's take a look at this next line. It is a y-intercept of -4. And it has the same slope. So we fall 2 and we run to the right 1 unit. Fall 2, run 1. Fall 2, run 1. And let's see, I'll put another tick mark here, make this -10. So we can fall 2 and run 1. Now, I don't know if my drawing gives it great justice here. A computer might do a little better job. Will do a better job, I'm sure. But these lines will never intersect. They're parallel. So this means no solution. And the way we often symbolize that is this symbol. It's an O with a slash. If you're familiar with the Ghostbusters movie, it's sort of it's like the Ghostbusters slash, except I think the Ghostbusters slash goes the other direction. So that's going to be it for today. We've covered the graphical way of looking at the solutions to these things. And basically, when we're dealing with systems of linear equations, we're dealing with a pair of lines. And lines will either intersect, they'll be on top of each other, or they'll be perfectly parallel, and they'll never intersect. If they intersect, there's one point where they intersect, and that's considered the solution. If they're on top of each other, well, then they're always intersecting with infinitely many solutions. And that's when you get a system of equations where the lines are really the same exact line. Exact, both in slope and in intercept. Now, when they intersect, they're going to have different slopes, different intercepts. Or maybe not different intercepts, but at least different slopes. Finally, when you have parallel lines, where you have maybe different intercepts, but the same slope. Different intercepts, same slope. You're going to have no solution because those will never intersect. The last couple things to talk about in this section, we'll do this on Tuesday, is how to do this algebraically. Because if you kind of notice, graphing can be kind of tricky. So can you do this without graphing? And the answer is you can. There's 2 other methods. There is what we call the elimination method or the addition method. And then there's the substitution method, which is kind of what we've done a little bit in Math 097. So we'll talk about that next time. Any questions? All right, well, good luck on your test. Again, the test is due Sunday. And if there's any hiccups, let me know. Other than that, have a wonderful afternoon.
Is 3.1 due today?
I'm going to extend that.
Okay.